Welcome everybody to the first part of the mathematics for week 5, where we'll be looking at a mass spring damper system, a second order system, but first describe it the way we are used to, and then describe it in terms of more general behavior. So if you have a mass spring damper system, this is the corresponding second order differential equation. And we know that if we wanted to solve this, we have an auxiliary equation, which is m lambda squared plus b lambda plus k, which is equal to 0. And we are looking for the zeros of this second order polynomial. And we get that lambda 1 and 2 are equal to minus b plus or minus the square root of b squared minus 4 mk over 2m. And there are three conditions that determine the properties of the solutions. And this is the way we did it in engineering, mathematics and modeling. The first situation is where b squared minus 4mk is larger than 0. Then this root is positive, and we know we get two roots which are not equal to each other, and they are real values, so these are not complex numbers, and the solution looked a bit like xt is a e to the power of lambda 1t plus b e to the power of lambda 2t. And we called this situation overdamped. Now the second situation is where if this is exactly equal to 0, so where b squared is equal to 4m times k, and this root disappears because its argument is 0. So the second situation is where it is equal to 0, then we get two roots which are the same, and they're still real values because we don't get the square root of a negative number, and we found the solution to be xt is equal to a e to the power of lambda 1t plus b times t e to the power of lambda 1t. Now the next situation is where the b squared minus 4mk is smaller than 0. b squared minus 4mk is smaller than 0, and then we get two complex numbers where lambda 1 is the complex conjugate of lambda 2, and they are complex, and we can write them as alpha plus or minus j times beta, and they're always going to be each other's complex conjugate because the difference is only a plus or a minus sign here. The solution is then xt is e to the power of alpha t times a cosine beta t plus b sine of beta times t. And we see that we can either have, so we get oscillations. That is always the case. If they are complex, we get oscillations, and we have some exponential term which can be exponentially growing. If alpha is 0, then the oscillations have the same amplitude, and if alpha is negative, then we will get decaying oscillations. Now in our case, if we look at the roots, the real part is minus b over 2m. In a mass spring damper system, the mass is positive, the damping coefficient is positive, and the spring constant is positive. So this term minus b over 2m, which will be equal to alpha, is always negative. So if we get a value for alpha that is non-zero, it will be negative, and we get decaying oscillations. So there are two cases we can separate. One is that if alpha is 0, so we get purely imaginary roots. So alpha 1 and 2 are equal to j times beta, which would be then the square root of b squared minus 4mk over 2m. So they will, which I will, well, I'll just call that beta. Actually, this should be the other way around. Otherwise, this will still be a negative number and it doesn't. So this is 4mk minus b squared. So this is now a positive number. The minus 1 that I've taken out of the root ends up here with j. Now, if there are only purely imaginary roots, we only get the oscillations and we call that an undamped system. And if alpha is less than 0, we call that an underdamped system. So we have an overdamped system, we have an underdamped system where we get oscillations which slowly, underdamped system where the oscillations slowly decay. We have an undamped system which is just a mass on the spring, and as there is no resistance or friction, it will just oscillate with the same amplitude indefinitely. And we have one other case where this is equal to 0, and that is called critically damped. And that is the boundary between overdamped and underdamped. Now, we have used specific names for M, B, and K. You can imagine that different systems might have the same behavior, but have different values for M, B, and K. And we want to introduce two concepts that will describe the system independent of the specific values of M, B, and K. And for that, we first look at the system where there is no damping. If there is no damping, if B is equal to 0, well, we are left with plus or minus the square root of minus 4mk over 2m. If we write that out, that we can take the 4 out and divide it, the square root of 4 out, which is 2 divided by 2, and what we end up is that lambda 1 and 2 are equal to the square root of k over m. So I'll just show that quickly. We end up with plus or minus square root of minus 4mk over 2m. We take the minus 4 outside, then we get plus or minus 2j times the square root of m times the square root of k over 2 times m. This 2 cancels. This ends up being square root of m, and we get j times k over, j times the square root of k over m. So I'll just take this off. Now, this value, so if we have this condition where they're purely imaginary, then we get oscillations which look like, solution which looks like xt is a cosine square root of k over m t plus b times the sine of the square root of k over m times t. And these are purely oscillations with a specific frequency. Omega n is the square root of k over m in radians per second, and this is called the natural frequency. And it's the frequency of the system if there is no damping. So we have this omega n here. You see that the natural frequency only depends on the ratio between m and k, so it is a behavioral property, not specific for m and k. Now, we have the natural frequency, and I would also like to introduce another term, which is the damping ratio. Which is the Greek letter zeta. And what that is, it is the actual damping in our system here we have damping coefficient B, so that will be the actual damping divided by the critical damping. And in our case, the critical damping is where B is equal to 4 times M times K. So this zeta can the square root thereof, which is equal to 2 times the square root of M times K. And so our zeta becomes the actual damping B over the 2 times the square root of M times K, which is just rewriting the square root of 4mk, which is the B value in this specific case. So we have the damping ratio zeta, and we have the natural frequency omega n, and we can rewrite our system. Well, first I'm going to do something here. I'm going to change this to x double prime plus b over m times x prime plus k over m times x equals f over m. So I've just divided by m, but that doesn't change the system in any way. But in this form, I can write it as x double prime plus 2 times zeta omega n plus times x prime plus omega n squared times x is equal to some force input. But the benefit now is that we can characterize all second order equations, differential equations, or second order systems of this type in terms of their natural frequency and their damping. And if we look at these, well, in essence 4 cases, we have 3a here and 3b here as 2 cases for the situation where we have complex roots and where we have oscillations. These occur in the specific situation where if we have an undamped system, then beta will be equal to 0, which also means that zeta is equal to 0. An underdamped system here, zeta will be between 0 and 1. For a critically damped system, we'll have zeta is equal to 1, and for an overdamped system, we have zeta is larger than 1. So the different situations here where we had to describe it in the coefficients of the second order differential equation, the mass, the damping coefficient, and the spring constant. Now we have, if you take the damping ratio, any second order system can be categorized by different intervals of values of zeta.